Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. In this video lesson for intermediate thermodynamics, we'll be looking at multiple reactions, and in this case, multiple reactions without phase equilibrium phase change. So if you have M independent reactions, then we've seen that the material balance gives you that the number of moles of species I is the amount you started with, plus the stoichiometric coefficients times extent of reaction for each of those reactions all added up. We also have that for a single phase, the equilibrium criteria for fixed temperature and pressure is that the stoichiometric coefficients for the species times the partial molar Gibbs energy for that species. The sum of those overall components will be 0 for every reaction in the reaction network. And we can use this, because they are independent reactions, to define that the equilibrium coefficient for each reaction is exactly what we would expect it to be. Let's look at an example for the multiple reactions in a single phase. So steam reforming of methane to make hydrogen gas is frequently used by, say, people working with fuel cells. So CH4 plus water can either make carbon monoxide and hydrogen or carbon dioxide and hydrogen. And we're going to carry out this reaction at 1 bar and 900 Kelvin. If the feed ratio is 4:1 water to methane, what is the equilibrium composition? So first, let's look at Gibbs phase rule for this. So Gibbs phase rule says the degrees of freedom is 2 plus the number of components minus the number of phases minus the number of independent reactions minus any restrictions that we have. So in this particular case, everything is a gas phase, and so therefore pi is equal to 1. And the number of components, well, I have methane, steam, carbon monoxide, carbon dioxide, and of course that product hydrogen, so the number of components is 5. And the number of reactions, these are independent, so the number of reactions is 2. And if I just plug those in, I end up with 7 minus 3, so 4 degrees of freedom. In this case, it makes it look like we've got a serious issue here, that these are, in fact, not a well-specified problem, because all I've specified is 1 bar and 900 Kelvin. So temperature is 900 Kelvin, pressure is 1 bar. But then we also did give a feed ratio. And so therefore the feed ratio of H2O to CH4 is 4:1. So that looks like 3 specifications that are going to make a fully specified problem. That still leaves me one more. And yet the assumption is that this problem was well posed. So what is missing? And what's missing is that this is really more complex than just simply saying this molecule to the other molecule is 4:1. Because in a reaction, they're breaking apart. And so what we have is that my O to C ratio is fixed. And my H to C ratio is fixed, or any two. Saying that the H to O ratio is fixed, it would be interdependent on these. So this one specification really is 2, because I have to look at the atoms, and I need to look at them so that I get an independent set. Okay? So therefore this problem is fully specified, that this restriction is truly 2, and then we specify a temperature and pressure. Our problem is now well posed. Next, let's look at the material balances. So for methane, let's say that it's 1 mole and 4 moles of methane and steam. So I start with 1 mole, and in reaction 1, I have X1 reacts, and in reaction 2, X2 reacts. And for the water, or the steam, I started with 4 moles. Again, X1 reacts away in the first reaction, 2 X2 in the second reaction. Hydrogen, I have none originally, but 3 X1 will be formed and 4 X2. And continuing for CO and CO2, CO is only in the first reaction, X1, and CO2 only in the second reaction, X2. And if I look for the total, it's 5 plus 2x1 plus x2, and I can use that to get y by taking n of species I over n total. So I now have my material balances. So in order to calculate the compositions at equilibrium, I'm going to need equilibrium constant data and then also for the temperature transition. From the book I was looking at, C sub P is A plus BT plus CT squared plus D times T to the negative 2 power times R, so that it's a dimensionless form. And the values for Gibbs energy of formation, heat of formation, A's, B's, and C's, and D's in the C sub P formula are listed here. And if you go through and look at this for each of the various reactions, then we get these values shown here, and for reaction 2, we'll get a similar sum with stoichiometric coefficients times these relative. So with these values calculated, I can calculate K sub A for each reaction independently by using the expression, the exponential of negative G for reaction, in this case 1, over RT, and in this case, getting the units worked out, this is negative 142,120, so 142,000 joules per mole over 8.314 joules per mole Kelvin, and the temperature in Kelvin for this data was at 298. And so we end up with 1.224 times 10 to the minus 25th. And if we repeat this for the other reaction, again, they're independent. I can simply do each one on its own. I end up with 1.272 times 10 to the minus 20th. And with such small values of Ka, we see that these reactions will barely proceed, which is why you would want to do this at a higher temperature. Now, if you use the formula in the book to calculate the Ka at the new temperature at 900 Kelvin, this is 1.25 for reaction 1, and for reaction 2, it's 2.93. Now, one more thing we need to put in for the pressures, the activities, right? Because each of these are going to be equal to a product over all my components of A sub I to the nu I for that reaction. And nu sub I have, clearly, it's specified right up here, in fact, on this page. But activity, so activity in this case, these are gases, and they are at low pressure, 1 bar. So 1 I over P over 1 bar is the activity expression to use for low pressures. But the P is 1 bar, so therefore it's just YI. And so if I do this, this is going to get me y of my CO, y of my hydrogen to the third power, y of my methane, and y of my water. And a similar expression, change the exponents to 4 and 2 there. And we get these expressions. Now at this point, I move the computer. And so if you do these on the computer, the temperature we're looking at is here. What you're going to find is that the X for reaction 1 is 0.332. And X for reaction 2 is 0.584. And then if you use those to evaluate all the various Y's, and honestly the way I did this in the computer was I actually set it up with the Y's. I didn't do like a clever algebraic expression for the K value. I just simply put in the values for Y and then had it vary X until it got the correct answer. And so we end up with these compositions here. Now, I borrowed this example problem from a textbook by Milo Koretsky, and you'll see that all these temperatures here, he did all of them, and I just borrowed his numbers. I only confirmed this one data point. If you look at these, you can graph these, and it's kind of interesting to see the effect of temperature. So in this first graph, we're looking at the conversion as a function of temperature. And reaction 1 is in blue, and it forms kind of a nice S shape here, right? Kind of forms an S shape. And reaction 2, the conversion of that, goes through a peak and then declines. So it seems like somewhere off over in this area is where you're going to get maximum hydrogen production. If you look at the Y values for this, what you're going to see is that the steam is going to decrease. That's this one here, this curve here. The methane also is declining, so that makes sense. And then all of our other products are increasing. And this is our hydrogen curve here. And so the hydrogen seems to actually reach a peak around maybe 950 Kelvin. But really, it's not all that different from about 900 Kelvin on. And so therefore you might save yourself some energy and do it operating more close to the 900 Kelvin point, just simply because you have to put in energy to get a reaction to be that hot. So just kind of interesting what you can look at when you get a reaction network. You don't get, just straight, as the conversion increases, I get a direct correlation. No, because multiple reactions are going to have increased conversion at different temperatures. So anyway, this concludes this video lesson. I thank you very much for your time. We are going to start looking next at what happens with phase equilibrium and chemical equilibrium combined. Thank you very much.